Welcome back to the Comptia Network Plus course. Metro Ethernet. Metropolitan Area Ethernet is a metropolitan area network, MAN, that's based on Ethernet standards and can connect a customer to a larger network and the internet. If available, businesses can use Metro Ethernet to connect their offices together, which presents another very cost-effective connection option. MPLS based Metro Ethernet networks use MPLS in the ISP by providing an Ethernet or fiber cable to the customer as a connection. From the customer, it leaves the Ethernet cable, jumps onto MPLS and then Ethernet again on the remote side. This is a smart and thrifty solution that's very popular if you can get it in your area. Wireless WAN Technologies. At one point it was taken as gospel that wireless technologies, especially WAN technologies, could never be completely acceptable, especially when compared to terrestrial technologies. Today that given is being challenged with a number of new technologies that can provide acceptable internet and even multimedia performance without a landline. In the following sections we'll look at some of the cellular WAN technologies and see how far we've really come in this regard. Cellular WAN. Cellular technologies have evolved since their introduction in the late 1970s. Terms like 1G, first generation, 2G, 3G and 4G are often used to describe significant advances in technology. First, I'll give a quick overview of the major developments and then we'll look more closely at a couple of the newer technologies, specifically what these technologies bring to the table and what they promise for the future. First generation cellular 1G was a voice-only analog network. The second generation 2G marked the switch to digital, which allowed voice for the first time, simple data such as text message. Fourth generation is still the most widely available, used globally at this writing, but things are about to change quickly. 4G allows high-speed voice and data, even internet. This is the type of network supporting most of your smartphones. GSM, or Global System for Mobile Communications, is a standard developed by the European Telecommunications Standard Institute, ETSI. It defines protocols for 2G digital cellular networks, which are used by mobile phones, and it's the default global standard for mobile communications and enjoys over 90% market share. 2G is still available in 219 countries and territories worldwide. The GSM standard was created to replace first generation 1G analog cellular networks and originally described a digital circuit switch network optimized for full duplex voice telephony. It evolved to include data communications at first via circuit switched transport, then through packet data transport via general packet radio services GPRS and EDGE, alternatively via enhanced data rates and GSM evolution, e.g. PRS code division. Multiple access CDMA is a channel access method that's used by various radio communication technologies. CDMA offers multiple access where several transmitters can send information and simultaneously over a single communication channel, allowing several users to share a band of frequencies. To make this work without a bunch of interference between users, CDMA relies upon spread spectrum technology and a special coding scheme in which each transmitter is assigned a unique code. Fourth generation 4G is actually still an emerging technology that has two variants, LTE and WiMAX. An organization called the Third Generation Partnership Project 2 G3GPP2 has set specific requirements that must be met for a system to call itself 4G. Its 4G project UMB was abandoned at this point in time. LTE and WiMAX meet these requirements. The goal of 4G is to provide data rates way beyond what's typically available today. Even so, uplinks for the mobile device to the tower will always be much slower, and the actual performance in the real world still isn't always so hot. I'll provide a few figures to clarify all this, but just know that 4G systems really should still be backward compatible with 3G systems most of the time to fully achieve the performance goals that 4G was created to meet. Oh, and obviously the device itself has got to be 4G capable to start with. HSPA Plus, Evolved High Speed Packet Access, is really considered a 3.5 generation technology. It does include all optional IP architecture, which is one of 4G's requirements, and it actually has greatly improved data rates over its HSPA forerunner. Because HSPA can use an all IP architecture, it has the potential to evolve into a true 4G technology someday. Because all the variables involved, it is difficult to get a set download and upload speed. WiMAX, worldwide interoperability for microwave access, is considered a true 4G technology, and it's based on the IEEE 802.16 standard. It supports both fixed tower-to-tower applications and mobile applications. It was originally designed as a last mile technology to deliver internet to areas where implementing landlines wasn't possible as an alternative to DSL and cable. But it has its challenges too. WiMAX just isn't compatible with 2G and 3G technology. It's pretty pricey and requires a lot of power. It also lags behind LTE in speed, with download link speeds of 5 Mbps to 6 Mbps and uplinks of 2 Mbps to 3 Mbps LTE. This brings us to long-term evolution, which is definitely the most promising of all emerging 4G technologies. It uses an all IP based core. It offers the highest data rates and is compatible with 3G and WiMAX, and it happens to have the best indoor coverage while maintaining high data rates all the way to the edge of a coverage cell. If that isn't enough for you, it also accommodates more devices in a given area and still performs really well by maintaining data rates of 7 Mbps to 12 Mbps on the downlink and 3 Mbps and 5 Mbps on the uplink. WAN protocols. Will be focusing on these 5 technologies in the following sections: ISDN, frame relay, PPP, ATM, MPLS. Integrated Services Digital Network. IDSN is a digital point-to-point WAN technology capable of maximum transmission speeds of about 1.5 Mbps, primary rate interface PRI, although speeds of 128 kbps, basic rate interface BRI, are more really within the SOHO environment. ISDN uses the same UTP wiring as POTS, yet it can transmit data at higher speeds. But that's where the similarity ends. The main thing that makes ISDN different from a regular POTS line is how it utilizes the copper wiring. Instead of carrying an analog voice signal, it carries digital signals, which also happen to be the key behind several more vital differences. First, a computer connects to a 128 kbps ISDN line via an ISDN terminal TA that's often incorrectly referred to as an ISDN modem. An ISDN TA is not a modem because it doesn't convert a digital signal from a computer to an analog signal on the subscriber line. ISDN signals are digital on the subscriber line. A TA is technically an ISDN compatible device that has one or more non-ISDN ports for devices like computer serial interface and RJ11 analog phones, which work to give these non-ISDN devices access to the ISDN network. Second, an ISDN line has two types of channels. The data is carried on a special bearer channel or B channels, each of which can carry 64 kbps of data. A BRI ISDN line has two B channels and has 23 64 kbps channels. On one channel can be used for a voice call, while the other can be used for data transmissions, and it's all made possible by time division multiplexing TDM on one pair of copper wires. The other type of channel is ISDN. It is also multiplexed onto only one copper pair. It's used for call setup and link management and is known as the signaling channel, D channel or delta channel. This channel has only 16 kbps of bandwidth in BRI and 64 kbps in PRI. To maximize the throughput, the two B channels are often combined into one connection for a total bandwidth of 128 kbps. This is known as bandwidth on demand interoperability group bonding or inverse multiplexing, but this still leaves the D channel free for signaling purposes. In rare cases, you may see user data such as credit card verification on the D channel. This was introduced as an additional feature of ISDN, but it hasn't really caught on. Some of the main advantages of ISDN are as follows. It offers higher bandwidth than POTS. Bonding yields 128 kbps bandwidth. There is no conversion from digital to analog. ISDN has the following disadvantages. Low latency, it's more expensive than POTS. Specialized equipment is required both at the phone company and at the remote computer. ISDN equipment isn't compatible to connect every other type of equipment out there. Why use ISDN if you can get DSL or cable? It's just a plain outdated technology. Remember that ISDN is a type of dial-up connection that must be initiated, so you know that ISDN is another form of high-speed internet access that delivers digital service on 64 kbps channels over conditioned telephone copper pairs. As I mentioned earlier, the device you must hook up to your computer to access ISDN services is properly known as an ISDN terminal adapter, which doesn't change from digital to analog like a modem does. It's only capable of changing between digital transmission formats. The box itself is about the size of a modem and happens to look pretty similar to one, and also like DSL modems, it has a phone jack and an Ethernet jack. You can connect a phone cord from the phone jack to the wall jack wherever your ISDN services are being delivered, and then you connect an Ethernet cable from your PC to the ISDN TA's Ethernet jack. Older, less capable TA used an Electronic Industries Association Telecommunication Industry Alliance EIA-TIA 232 serial port for PC connectivity. It's exactly these similarities that cause people to confuse ISDN TAs with standard modems. So I'm going to leave it here today for this video. If you like listening, please consider like, share and subscribing. Thank you.